We have problem 4, the Burj Khalifa, the tallest building in the world, 828 meters tall. So we go to the top, we drop
Here
a
we
penny.
go.
How long will it take to hit the floor? I want to give you an opportunity to go ahead and try this out without me. Okay, I leave you the answer. It's rounded. I
Perfect.
believe it should be like 12.99 seconds. But why don't you go ahead and pause, try that 531, see how far you get with this. So pause me. So if we do the 531, we go ahead and list the 5 variables, v, v naught, g, t, and delta y. Recall that the a has been replaced with g, and the delta x has been replaced with delta y. Those are the 5 right there. They gave us 3 things. Actually, they only gave us 1, right? The displacement. However, this is free fall, so the gravity is going to be 9.8. And this was dropped. Drop means that this fell from rest. So V naught is 0. There's your 3. The one thing that we're looking for the time. How long does it take? Which means we do not need a V. That boils it down to the second kinematic. However, V naught is 0. And so this eliminates this entire term. We end up with a simplified version of this equation. And we're looking for the time. So we're going to solve this for time. We've done it on a number of occasions, but let's do it again just in case. I'm going to go ahead and multiply both sides by 2. We're going to get rid of this fraction first. Doing that, these cancel out. I get 2 delta y is equal to gt squared. Remember, we're solving for t. We want to get this variable t by itself. However, it's being multiplied by gravity, so I'm going to divide both sides by gravity.
Perfect.
Some of you may not be as comfortable with algebra as you should be. We don't always square root everything. We only square root when we're solving for a variable, and that variable is squared. So in this case, I have a t squared, and I need it to be only t. So I'm going to square root the entire thing.
Perfect.
We go ahead and replace everything inside of it. Delta y was 828 meters. Gravity is 9.8 meters per second squared. And some of you have fallen into some bad habits. I need you to pick up some good habits again. Put this all into the calculator at one shot. Okay, and you should be able to get, I believe I got 12.9999, whatever. And that ends up being 13, your 13 seconds. Okay, not bad. If you want a nice little challenge, find out how fast is it going, right? How fast is this penny going by the time it hits somebody or hits the ground?
Here
That
we
was this far
go.
away. Now, some of you were struggling before with scientific notation. What this means is it means that you're going to move this decimal over 4 times to the right. Why is it to the right? Because it's positive. If this were a -4, you'd move it 4 spots to the left. But this is a +4, so I move it 4 spots to the right. That's 1, 2, 3, 4, which means we have that many zeros. So that's 36,000 meters away from the Earth, or 36 kilometers away from the Earth's surface. Okay. Now, our answer isn't going to be exactly true because gravity, as we've discussed earlier and many times, gravity actually changes the further you go away from the Earth's surface. So technically, gravity was a lot less from the point where he jumped at. And so as he's falling towards Earth, actually the gravity would be changing as he comes down. It would be increasing. Okay. Uh, just for your information, those of you that are curious and wanna look into some of these things, we say that the change in distance, right? The change in distance is velocity. We say the change in distance is velocity. Change in velocity. Now, what I mean by change is change with respect to time. So the change in distance with respect to time is velocity. The change in velocity with respect to time is acceleration. The change in acceleration with respect to time is a jerk, and then the change of a jerk with respect to time is a jolt. Okay, and these two in particular are important when it comes to roller coaster physics. So if any of you are interested in going into that kind of a field, you end up dealing with changes in accelerations, right? And this is where this comes in. So, but for the simplicity of this problem, we're going to assume that it's a constant 9.8. So, spoiler alert, the answer you're going to get is actually more than realistically happened. Although this guy did break the sonic barrier himself without a plane. I went faster than the speed of sound, definitely. Okay, so he was definitely going at a very massive amount of velocity. So if we do the 5-3-1 for this problem, this is actually a pretty nice problem. Usually the case in real life, whenever you do a real problem, you get a lot of data, and as a result, you have a lot of options because you have so much data. So in this case, we have a surplus of data. We have extra data. If we do the 5-3-1, we list all 5 variables, and we have identified the 3 they gave us, when in reality we had more. He started from rest, right? He just leaped. He didn't even leap, he just kind of just tipped over. So V naught is 0. We'll assume the gravity is 9.8, although at that elevation it is a lot lower. Okay, but we're simplifying the problem for you. The time he was in the air before he released the parachute was 4 minutes and 19 seconds of pure free fall. Okay, if we convert that, we get 259 seconds. And then we know the displacement was 3.6 times 10 to the 4, which is 36,000 meters. The one thing we're looking for is his velocity. There were multiple ways to get this problem done. The simplest one would be with the first kinematic. We simply plug everything into the calculator, and we're going to get that V is 2538.2.
Perfect.
You have one of these seconds, cancel out one of these seconds, leaving you with the correct meter per second. Our last problem, a classic problem, the beanbag. What is very amazing about these vertical freefall kinematic problems is how little they give you, right? They only gave us one number, which means you have to assume multiple things, a couple of things. Let's go ahead and draw a diagram first, a simple one. Notice that this is going straight up and straight down. However, it's kind of hard to see what's going on when we do that. So I'm going to go ahead and draw this parabolic. It was caught at 2.2 seconds later, meaning that it was released at this point, and as we travel this, the timer is going, and then we click the timer when we catch it again, and that whole trajectory is 2.2 seconds long. Now, you don't know much about parabolas perhaps at this point, but a parabola has symmetry, meaning that it's a mirror image of itself, which means I could cut this in half and it would be exactly the same. So in other words, however fast I launch it here is however fast it would be going at this point right here. At this point, this velocity would match this point. At the midway point, this velocity would match the midway point. And not only that, but also the times would match as well. Okay, so to get from here to here would be the same distance as it would be from here to this point. In other words, then, what we can use to our advantage is the idea of symmetry, meaning that if I cut this in half, it took it 1.1 seconds to go up and 1.1 seconds to go down. In other words, that means at this point up here at the apex, it took it 1.1 seconds to get to its maximum height. We also know that at the apex, the velocity would be 0. And we also know that V naught would be going upwards this way. However, gravity would be going against it. One of the reasons why we are doing this problem is the idea of positives and negatives. If my V naught is going to be positive going upward, then my gravity will be going negative downward. Or if I want to do it the other way around. You have to keep in mind that this beanbag is going up and gravity is going down. So just like with our Newton's laws, with our free body diagrams, if they are going in opposite directions, we must have opposite signs. Okay, so in this case, I want to assume up is positive and down is negative. And we're only going up to the apex. So don't worry about the whole trajectory. I'm just going from here to here. What I changed was I'm not using the 2.2 seconds. I'm using 1.1 seconds. And that's because I'm only figuring out how high did it go, and I only need half the time. You might want to make a big point about this in your left column. Why are we using 1.1 seconds instead of 2.2 seconds?
Here we go.
Now, with this in mind, notice I have the positive going up, the negative going down. I have time is 1.1 at the apex. At the apex, the velocity becomes 0. I do V naught G T delta Y. I have V is 0. We have gravity is negative 9.8. We have time is 1.1 seconds. We identified the 5, the 3 they gave us. We are looking for how high it went, delta Y, which means I do not need V naught. This is a great problem on many levels. So what happens is that we cannot solve for delta y without doing some extra legwork. So we need to actually find out what V naught is, because if you look at your three kinematic equations, they all need V naught, and V naught is not zero because the final velocity is zero. So let's find V naught. We can easily find V naught using the first kinematic. If I solve for V naught and get this by itself, I would subtract GT from both sides, not divide, because it's being added. The opposite of addition is going to be subtraction. So V naught is V minus GT. You'll notice very important here that the negative, we have a minus, but then a 9.8 also had a negative, and that gives you a positive V naught. And it came out positive, right? We predicted that it would be positive. That's very important. Now we have everything we need to go ahead and find delta y. So here's our setup for delta y. It's extremely important that you have this negative in here. Otherwise, you end up adding everything and you get a number larger than is the correct answer, a very different number. So that negative has to be there in place, because that's what we originally claimed to be, because it was going opposite of the initial velocity, which we were going to assume is positive. So we said up was going to be positive, down is negative, and therefore this negative has to be in place right here. Otherwise, you'll get a very bad answer. Do your best once again to please put this in a calculator in one step, not multiple steps. I've been grading some assignments, and there are errors because some of you are going in steps and things are getting rounded along the way. You should get 5.929 meters. Now, for those of you who are super cool, because you can, let's do this again with the third kinematic. The third kinematic is V squared is V naught squared plus 2 times G times delta Y. If I get the delta Y by itself, we've done this numerous times. We would subtract the V naught squared first from both sides.
Perfect.
And as we do this, by the way, you should get the same exact answer again with a different kinematic, right? We would divide both sides by 2G, and we get the delta Y is V squared, which is 0, squared, minus the 10.78 meters per second squared, divided by 2 times negative 9.8 meters per second squared. And I would propose to you that if you're really comfortable with your calculator, you should be able to put this all at one shot. And not only that, it'll give you the exact correct answer. And it won't be negative, it'll be positive. So regardless of which kinematic you use at this point, whether the second kinematic or the third kinematic, you would have gotten the same answer with the same exact sign. Summary. How did gravity affect the above three problems? How does the 531 differ with free fall problems?